Hello, I'd like to welcome you to today's seminar, and first I'd like to give a plug for our speech next week by Fernando Pineda from the APL Labs, Sir Johns Hopkins, who will be speaking at Bayesian Networks. Dr. Kehler is, I guess, someone I've known for 9-10 years now. He got his undergraduate degree at Penn, then prior to going back for his PhD at Harvard, he was one of the chief scientists at SRA in the NLP group. He worked for a summer in the machine translation team at IBM with Bob Mercer and Peter Brown while at Harvard. And for the past 4 years, he's been a principal scientist in the artificial intelligence group at SRI. A great pleasure. I think
David, thank you very much for inviting me. Turn this on, right? Let me apologize in advance to the camera crew. I have a tendency to walk around when I talk. I've been criticized for this on numerous occasions, but I'll do my best to stay in one place.
No, don't, they don't focus on you, focus on you.
Oh, okay, good. A wise idea in general. So I'm going to be talking kind of in general terms about an application that's been a popular one, or at least driven kind of a niche community in natural language processing, that of information extraction. So I've designed the talk in hopes that maybe some of you kind of know what information extraction is, but don't know a lot of the details, or maybe you don't know what it is at all, but hopefully aren't as familiar with it as somebody who's been in the community for a while. So what I'll be doing is spending some time introducing information extraction. What's the definition of the task? How are these systems evaluated? And what has come to be essentially a standard system architecture for such a system. I'll briefly go over some previous work in applying learning technologies to information extraction. Although learning is yet to be the dominant paradigm in this area. I'll then talk about some rather ambitious and actually fairly unsuccessful experiments in learning a high-level process in information extraction that applies at the level of discourse, that is between sentences. And these failures actually, for certain reasons I'll go into, inspired me to look a little closer at the nature of the evaluation metrics that are being used in the community, which will be quite revealing. And then so I'll just summarize with some ideas for future work and lessons learned in all of this. So first off, what is information extraction? What do these systems do? They essentially take as input streams of natural language, analyze it, trying to identify information that's relevant to some pre-specified topic, and outputting some kind of formal representation of that information, typically in the form of database templates. So it's kind of a more complex task than information retrieval, in that you're not just bringing back documents or sentences, but you're kind of figuring out who did what to whom, where, and when, and representing that somehow. But while it perhaps requires full-blown natural language understanding in the limit, it's a nice task to drive research in that you can get pretty far without doing a lot of the kind of solving the AI complete problems associated with that, inferencing and so forth. What's driven work in this community is what's called the MUX. It stands for Message Understanding Conference. A lot of people think the C stands for competition, and there's reasons for that. Although the government likes to tell us it's not a competition. It's a cross-site evaluation. There's been 7 of them over the last, over an 11-year period. I'll be focusing on MUX 6, which happened in '95. The main task being to extract information about people moving in and out of high-level positions at companies. So we're reading Wall Street Journal data and trying to find information about changes in upper management corporate personnel. There are other lower-level tasks that I won't discuss at all, but you may have heard of them. There were 9 sites that participated in the scenario template task, although there's actually 11 systems, because one site contributed 3 systems. So I'll make this more concrete with an example from the the MUC6 development corpus. So I won't read all this to you, but essentially there is an extractable event in this document. Because here we find out that the chief executive officer of Star TV resigned. Now, so far, it's not an extractable event because we don't know who resigned. But later, we have a reference to the executive, Julian Mounter. This is a reference that we can understand as referring to this CEO. So now we have a person, a position, a company, and we know whether they're coming or going. So we have an extractable event. Now, other information you may see about people in high-level positions isn't extractable, like Murdoch's being chairman and CEO of News Corp. Since he's not coming or going from that position, it's not an extractable event. The output representation for the MUC looks like this. It's essentially a hierarchical template structure. So a succession event is a top-level representation for an event. There's three kinds of fills that you have in these slots. You have pointer fills, like the succession organization, which essentially just have an ID for another template, which has its own set of slots. You have string fills, like CEO, where you're essentially pulling it out of a text. So that's the post slot. And then you have these slots like reassignment that are called set fills. So you have a pre-specified finite set of values that can go in one of those slots, and you have to pick the right one. So here we have essentially events which are centered around organizations and posts, and then point to one or more in and out templates that are centered around a person and the direction that they're moving in. Are they leaving or coming into the job? And then you have various other types of slots. But this requires that you pull information from different parts of the text and represent it together. So in one place they say Star TV, and that's the real name. In another place they refer to as Star, so we call that an alias. Another place they call it the satellite broadcaster, so that's what's called a descriptor. Type is just a slot set fill. Here again we have names and the aliases for people, and we even keep track of their titles. So these systems are evaluated in a two-step process that interleaves an alignment procedure with a scoring procedure. So essentially, you may have many events represented in an answer key for a document, and your system generates many events. So the first question is, what event descriptions that the system generates correspond to what event descriptions in the key? This isn't necessarily a trivial question because there's no slot that could uniquely identify an event. So that's the alignment question. So the question is, what templates are possible, are candidates for alignment? And the community deliberately chose a very weak alignment criteria, just saying if two templates share one slot value, no matter what slot, that's a candidate for alignment. Beyond that, then you do a search where you score that alignment and then try to search among different alignments, essentially in a greedy fashion, trying to find the alignment that maximizes the score. And because it's essentially a greedy process, an optimal solution isn't guaranteed, but we kind of expect one because while graph matching isn't an NP-complete problem, these graphs aren't that large. The actual metric is being used as well, first we borrow from information retrieval the notions of precision and recall, in this case on slot, measured at the slot level. So precision is the percentage of slot values that the system creates that are correct, that is, that are in the key. And recall is the percentage of slot fills that are in the key that the system got correct. Now, of course, in evaluations, two numbers is one too many, so they have a way of taking a harmonic average of the two, called an F-score, as formulated here. Now, this beta variable essentially it gives you a dial for which you can specify how much you care about precision versus recall. The only numbers that anybody really talks about are where beta equals 1, that is equal importance between precision and recall, which give you this equation. The effect of this equation is to average precision and recall, but in a way that penalizes large disparities between them. So if your precision and recall is both 60, your S-score will be 60. If your precision is 70 and your recall is 50, or vice versa, this number is going to be somewhat less than 60. So here's an example output we might have for our example system. So we generate the correct event here, and you don't need to kind of look at all of this. But we miss a few slots here that are going to affect our recall. We generate a couple spurious slots here that are going to negatively impact our precision, and we get some incorrect slot fills that do both. So we have essentially 8 correct slot fills here out of 13 that we generated, giving us a precision of 0.615, and those 8 out of 15 that are in the key, giving us a recall of 0.533. And if you use the S-score equation to combine them, you get an S-score of 0.571, which, as you'll see in a couple slides, is essentially state-of-the-art performance for an IE system. What actually happens with these MUX, or at least in MUX 6, is the big day comes and you find out essentially what the task specification is. You're given 100 example texts, you're given answer keys for those 100 texts, and you're giving the scoring algorithm that will be used to test you on the blind data, so that you can use that to iteratively gauge your process. You're then given a month to kind of run around and try to do the best you can, freeze your system, and then they send you 100 blind texts. You run the system and send the results back, and they score them, and they tell you how you did. How did people do? Well, out of the 11 systems that were in MUX 6, we got scores from around 33.5 to 56.5. Where the top 6 systems went between about 51 and 56.5, and in fact, a somewhat strict statistical significance test tells us that in fact no pairs of those systems are actually different. There's a fair amount of room here with nothing to be inferred. They did a little annotator study on 30 texts and found that the annotators agreed at a level of 83%. So that's kind of a theoretical best that you can expect your system to do, kind of measuring how concrete the task is. I won't really step through these quotes, but essentially what they say is that the MUX have been very influential, been the primary driving force of research and information extraction, and in fact are the natural language understanding-ish evaluation that by far we have the most experience with, 11 years worth. So these tasks and metrics have been hashed over many times. Just want to make a note about the state of the technology. So I've discussed the task and the evaluation. Now, what do these systems look like? Well, like other fields, or I should say applications within language processing, went through this phase where we started off where essentially, when the task was introduced, what everybody did was take their general natural language understanding systems that they had built, that did general parsing and domain-independent semantics and discourse processing into some kind of general meaning representation, and they glommed an extraction engine on the end. And those systems didn't perform very well. Essentially what would happen is by the time you went through all these complex forms of linguistic processing, somewhere along the way you would have made a mistake that made it so that you didn't extract the right piece of information. And in some cases, the information would be like right in front of you. John Doe was named president of Apple. There it is. And somewhere along the line you would misparse it or something and lose it. So what people then did is kind of took an approach that drew a straighter line between point A and point B, taking a shallower type of approach. One of the first such systems to do this was developed at SRI a few years before my time there, called FASTIS, which has mainly 2 main modules. A series of pattern recognizers that incrementally does a sentence-by-sentence analysis, pulling out relevant pieces of information. So I've dummied up a little fake passage here. John Smith was named president of ABC Corp. He replaces Mike Jones. So the template structure that we output for MUC is too complicated to work with system internally for a number of reasons. So we defined a much simpler version where we have what we call a transition that essentially says, with respect to a job at a company, who left and who's coming in. So from this sentence, we would generate a representation that John Smith became president of ABC Corp. And in fact, we'll hypothesize that somebody's in fact leading that position, but we don't know who. Now, somewhere later in the text, we see he replaces Mike Jones. Well, we have a module, an auxiliary module for co-reference that'll tell us that the he refers to John Smith, at least hopefully, if everything works right. But all we know then from that sentence is that Mike Jones wasn't somewhere that John Smith is now at. There's no mention of the company or the position in that sentence. So what we currently have here is not an adequate representation for what we want to extract from the text. There's this intersentential dependency, and that's the job of this template merging algorithm, which essentially comes along and happily sees that these two templates can be unified together without any contradiction. And we'll take them and go ahead and do that and create this representation that Mike Jones was in the position of president of ABC Corp. And then we can turn that into the muck representation, and then we would get it right. Okay. As I mentioned in the introduction, the dominant paradigm in IE is still hand-coded systems. And that's not to say that hand-coded systems don't have all the standard disadvantages. That is, they do require a lot of expertise to build. It takes a long time. It's error-prone. The results can be brittle. Not brittle in the way that some of the systems that were developed in the 80s are brittle, but still, you don't tend to recognize things that you didn't think of before. The main reason is some of the problems with taking what's the dominant learning paradigm in computational linguistics and applying it to some of these problems. As far as the end-to-end, that is supervised learning. So as far as the end-to-end results, these training data don't tend to naturally occur, these template structures. And they're hard, they're very costly to produce, and frankly, if you had to do this yourself, take my word for it, it's murder. I was telling some of you earlier that we actually had a contractor that quit on us because we wanted them to produce keys. It takes a long time and is error prone itself. Even if you had a large body of these templates, the connection between the surface text characteristics and the end product can be tenuous at times. There's normalization that occurs. Again, you have to find information from different parts of the text that end up in the same place in the template representation. There's a lot going on to expect a learning algorithm to figure out what the connections are. So then you might move to encode training data for each subtask in your system. Just go ahead and dump representations and do annotations. But as we'll find out later, what you think these modules might be doing for you in terms of the end-to-end task isn't always representative of what they are doing. And I'll talk about that a little bit more later. And lastly, the downstream modules of these systems are dependent on the quality of the output of earlier modules. So what tends to happen is you'll annotate data for the downstream models, and meanwhile you've got somebody down the hall who's changing the input modules. And by the time you're annotated your data, it's no longer representative of the input that the modules get. So the keys become quickly obsolete in any kind of realistic development setting. Now, despite those drawbacks, people have done this kind of learning for modules of their system. And what you end up seeing is the closer the task is to the text the characteristics of the text, the better your modeling is. So, for instance, PBN has a Markov model-based system for doing name recognition that's only a couple points under the best hand-coded systems for all intents and purposes. It's fully competitive, and it has a number of other advantages in terms of portability and so forth. Pattern recognition, it gets a little more murky. Generally, nobody's been able to robustly learn patterns in a muck-like setting. They've either had to they've either had to address a much simplified task, or have some human in the loop that goes through and filters out by hand patterns that are learned by the system. It's tough to find a general comment to make about work in co-reference. These three works here are quite different. but they all have somewhat limited scope. And while they can be shown to improve and make different assumptions, but while they can be shown to improve certain baselines, they haven't, had a lot of payoff in terms of the end-to-end system. So again, the more we get into kind of higher levels of linguistic processing, the further we are from the text, and the less competitive the automatically formed systems are from the hand-developed systems. Okay. Despite all that, I focus my attention on this discourse level mechanism, this merging process that I described before, which essentially seeks to find cases in which you have event descriptions that are actually partial descriptions of the same complex of events. And it's a crucial process to do in an information extraction setting where you need to represent the right number of events in your output. Now, this is the crudest possible approximation to a task that actually people use a lot of inference and knowledge to do. All it does, as I said before, is simply test for templates. If you create a template from the extraction module and it sees whether it can unify this with some previously created template, starting with the most recent first. If it can do it, it goes ahead and unifies. It uses no knowledge or smarts or anything to determine whether this is a good idea or not. Yet it seemed to be working okay for us, at least compared to anything else we tried. Nonetheless, when we did an error analysis of our MUC6 data, in fact, almost all of the errors indicted this merging process, at least in part. So it seemed like a potential gold mine for improving our system. So just to make this more concrete, the other slide you saw that looked like this was a story of a merge that happily worked. But it could have been as easily in this case, where down the second sentence says, Fred Johnson left ABC after Smith eliminated several perks for upper management. So it's very likely the fastest, or a system like it, will find information in Fred Johnson left ABC and say, okay, there's a person in an organization in a start state. But it's not going to see any relevant information in the rest of this material. Now, when we read this, it's pretty clear to us that, in fact, Fred Johnson was not the president of ABC, and Smith is not, therefore, not replacing Johnson. Johnson's in one of these other jobs and left later. Yet that's exactly what the inference, the inference would be that the merger will happily make in unifying these templates and ending up with this output structure. So we want a way to kind of block these bad merges, but still keep the good merges. So I tried to do this by eyeballing the data, which turned out to be a frustrating process because I dumped these extensive traces of the merging behavior, and I keep finding these constraints, these relationships that I could say, boy, every time these pair of templates had a certain property or a certain relationship to each other, the merge is always a bad one. So I go and implement a constraint in the system, run the system end to end on the training data, and the score would either like stay the same or go down a little bit. So this was puzzling, and I thought, okay, well, maybe I'm being misled by the relatively small sets of data that I'm analyzing. Let's try a learning approach to this. So here I'm just kind of doing some preliminary experiments here. So I constructed some feature sets, some questions that a learning algorithm could ask about the templates and trying to decide whether it's a good idea to merge templates or not. And out of necessity, these are pretty crude features. They ask about, say, the distance between the phrases in the text that gave rise to the templates. Under the idea that it's templates that were created close together are more likely to merge than one that, say, appeared in paragraph 1 and another in paragraph 5. The content, how are these well-populated templates? Do they overlap in content? If they do, then that's probably a good sign that they're reliable and should merge, and not if not. So I dumped a corpus of every merge that the system tried from when applied to the training text. Try to code it up a classification tree in the style of Bryan et al. And a max entropy modeling technique, the IBM technique that you're, I'm sure, very familiar with. Try a threefold experiment and found that according to my annotations, the learned mergers were only making about a quarter of the mistakes that the original merger was making. So that sounds great. It looks like I'm actually was a little surprised. We found some structure in this data. So I went ahead and trained on all the training data, and then changed the merging algorithm in fastest to be directed by these new learned classifiers. And sure enough, when you run a system end-to-end, you get no performance, or even a little decrement in performance. And this was even on the 100 development texts that gave rise to the merges that I annotated to begin with, right? This is very strange. So for starters, it seemed to show that what I thought merging was doing for the system, and what everybody else at SRI thought merging was doing, wasn't actually what it wasn't what it was doing in helping us improve our score. And you can see some cases where this might be true. So let's say there are cases where on a text we incorrectly extract templates for 2 events. They're both wrong, and if we output those events, we would get a bad score. But then the merger might happily come along and incorrectly merge these 2 incorrect events, giving us 1 event that's going to negatively affect our performance. And it's actually an improvement to do something like that. In any case, at this point, I thought, okay, well, if we're interested in improving our F-score, given this experience we've had, we should have F-score being driving the learning process. So I tried something called indirectly supervised learning. So the idea is you have a little parameterized model embedded in a system, but you're trying to train that model from end-to-end system results. Now, I'd like to say that I did something really clever here, but it's very hard to figure out in a system like Fastest how to do something, because it's very hard to kind of impose a mathematical model on what's going on in this system, believe me. There's so many variables coming into play, and including the alignment procedure and stuff that's kind of out of our control, that I had to fall back to a pretty general technique. So I actually borrowed this idea from the clustering literature, hierarchical commutative clustering, where you group things together iteratively in accordance with some similarity metric. Now here, similarity is kind of being used in a strange sense, because what I'm going to do is use that to group templates that are candidates for being merged. And when I cluster templates together, I'm actually going to go ahead and merge them. So all my sets that I'm clustering together at any given time are only going to have 1 element. And the idea then is to parameterize the similarity metric and try to tune the parameters. Okay, so this is actually kind of an adaptation of the exponential model used in maximum entropy modeling. I won't go into detail except to say that there's a parameter here for each of these questions that the learner can ask, and this actually does give you a probability as a result. So as I was saying, I had to take very general techniques. So I did a greedy search technique and an annealing search, where you simply would permute the existing similarity metric and then run the system end to end. If it improved your performance, you kept the new metric. And if it hurt your performance, if you're doing a greedy search, then you would throw it out and go back to your old metric. And if you were doing an annealing search, you would still accept the new solution with some probability that's inversely proportional to the decrement of performance that you got. So that it's just a way of staying out of local maximum. Well, I ran a number of experiments and often got learning curves like this when I use curves in a loose sense. It may look like there's actually a slight bit of a curve here, but if you look at, so here we have iterations on the x-axis and f-score on the y-axis. And if you look at this, you can see that this is essentially a straight line. We started off at about 58.7. We got down early as far as 57.7, and we ended up at about 59.8. We squeezed about an 1 point of f-score above a randomly generated metric, right? This is on the training data, right? This is like, you're probably not going to buy me anything on test data, right? So this is like, okay, now I'm really getting frustrated, right? I tried eyeballing the data, I tried supervised learning, I tried this, and nothing's working. And I thought, boy, I need an explanation here. The one thing that all these experiments have in common is that my definition of success has been, given to me by this S-score metric. Maybe I should look at that a little more closely. So let's look back at our example passage. So recall that the correct thing to do was to generate this event of Julian Mounter becoming CEO of Star TV. Well, it turned out that Fastest made two humongoid mistakes on this text. First, it completely missed that event. Okay, completely, got nothing. Second, to add insult to injury, for some reason it thought that Rupert Murdoch was actually coming into the job of CEO of News Corp. Luckily, it missed the chairman part, or if it had done that right, we would have gotten even worse, right? Okay, so it missed the correct event entirely, and it generated a garbage event. So this is what happened. Recall that there's pretty loose criteria for aligning templates, right? So let's start at the bottom. Well, we're supposed to get Julian Mounter, but instead we got Rupert Murdoch, but in typical Wall Street Journal style, it referred to them both with the title Mr. So we get a point for that. Now, because we get that one correct slot, we can now align these. Essentially, the scoring algorithm says these are the same people, which means the fact that up here we point to these two templates in the keys, we get a point for pointing to them for that slot. Because there, if you have a pointer fill, you get a point if they're pointed to things that are aligned. If we look at the organization, we screwed that up too, wrong company. But we got right the fact that they're both companies. Now, in the Mach 6 training data, out of 117 organization templates, 115 have org type company. Guess what rule people put in their systems, right? You generate an organization, it's going to have type company. Well, we matched the slot. Those must be the same companies. So in fact, when we go up here and see that we're actually both pointing to those companies up here, we get a point for that too. Now, up here, on the job, this slot was kind of a mess, and most systems just always generated unclear because it really was unclear, and it was such a mess that even the humans didn't know, who were annotating this stuff didn't understand it, so they tended to say unclear. Well, now we have two slots right here, which means that these two in and out templates align, and so we get a point for the pointers. It just so happened out of luck that both of these events involved an CEO. Now, the only jobs that mattered for this were CEO, president, and I think vice president, and chairman. So we did get lucky and get that right. And then, of course, there's a high level, since there's more than one event, there's actually a place to store all the events. And since we actually aligned these events correctly, we get a point for that, and let's see. That would be 8 correct out of 13 that we generated and 15 in the key, giving us a score of 57-1 again, right? The same score we got the earlier time. State-of-the-art performance, right? This isn't exactly, I should say, this is not exactly what Fastest generated for this. I modified like one or two slots just to make the point, but it's close, right? We did really well in this message after completely bungling it. Now, you might say, okay, all right, that's cute, that's funny, but it's still kind of harmless, so we got a little fortuitous credit, but no big deal. And there's no reason, maybe this affected how systems were ranked, but there's no reason to think that any system would benefit from this effect more than any other. But it is a problem because of this role of evaluation in the development scenario, right? So a very typical thing to do, when you're hand coding one of these systems, you often find events where the extracting the right event would just be too hard linguistically, right? It's just, you're on the tail end of the zip curve. If you encoded a pattern, you would never see an example that pattern matched in test data, and you could screw something else up, so you just punt on it. but maybe you can fix the bug that overgenerated the garbage. Now, usually, what happens if you do nothing to your system except, get rid of irrelevant garbage, you expect your precision to improve and your recall to stay the same. Right? So imagine in an information retrieval setting where if you made a change that did nothing but take some irrelevant documents that you were previously saying were relevant and now correctly categorizing it as irrelevant, this is what would happen and your F-score would go up. Now this is a kind of a degenerate case because once you take away, so if you get rid of that garbage event, essentially your recall goes from this to 0. These can't become undefined because there's also a 0 in the denominator. These are both 0 over 0. But the contribution from the overall system is essentially 0. To make this a little more concrete, so we don't have these zeros, let's just suppose we had a case. So here's our template in the key with Julia Mounter. Here's our event that we generated with Rupert Murdoch. And let's just suppose that there was another part of the message where we had an event in the key and we generated one that we corrected an event that was correct. We generated an event that was correct, that appropriately got aligned up here. And we're not going to do anything that's going to change that. But for the sake of argument, say that this had the same properties as our original example. That is that we got 8 right out of 15 in the key and 13 generated. What's going to happen if we get rid of this garbage event? So what we're doing now when we change our system is to get rid of this irrelevant garbage and keep everything else the same. So again, the recall should stay the same, but the precision should get better because we're not generating the garbage. But what actually happens is the precision stays the same and the recall gets cut in half. And the F-score for the passage goes down by 0.2. The opposite thing happens too, of course. So say you could write a rule that got the correct output, or some of the correct output for the event, but you didn't want to write a rule that got rid of the overgenerated event. Because maybe that rule was doing well for you on other messages or something. So you expect, nonetheless, an improvement. So say we wrote a rule and we generated 12 slots. There were 15 in the key and we got 9 right. So that would give us an F-score of 2/3. So what actually happens here when you add this event? Then essentially the right thing happens. This event will get aligned to the correct event in the key. So that's good. But now, the overgenerated event will actually get scored as overgenerated. And so your precision will go in the tank as your recall stays to what it would have been if you generated that event alone. And again, the feedback you get from the scorer was that this was a bad change. So typically when this kind of thing happens, what you do as a developer is you take out the change that caused the score to go down. But in both of these cases, these were changes that anybody, given the research, the goals of driving research that this whole task was designed to promote, anybody in the field would agree that these are all uncontroversially positive changes that the S-score is telling us are bad. Similarly, you can imagine having a learning procedure, right? A greedy search. Let's say we're trying to learn patterns. And at any iteration, you could add a pattern or you could delete a pattern. Right? So here, what you really want to do is you want to add a pattern that gets the right, that generates the right output, and delete the pattern that generates the wrong output. But if you can only do one of these in an iteration, you're never going to get there. Because either thing that you do first, the S-score is going to tell you that your performance went down, and you're not going to accept that permutation. So essentially, if we had the alignment, the key point here is that if the alignment was done correctly, none of these things would happen. Either move that the learning algorithm could make would improve the score, right? So hopefully, at this point, at least you might be convinced that This is like a bad property of an evaluation. Like, positive changes should not result in negative feedback from the metric. And this could have an effect both with hand-built systems and misguiding system development, and also with automatically trained algorithms, of course. It seemed like for Muck, and this was kind of supported by the merging experiments we did before, that what really mattered was that you do enough merging to get about the right number of events. It mattered much less what the contents of those events were, because they would still typically get aligned with something and we get some amount of score out of it. Now the question that always comes up though for somebody in the Muck community is like, okay, so you made your point with this nice little cute example. Does this actually make a difference? Is kind of Muck a crock because of this? And I actually initially thought that this probably was, a fairly rare example. That it probably wasn't that pervasive. But nonetheless, decided to do an experiment. The scoring algorithm did allow you some flexibility to design a stricter alignment criterion. It's just that nobody tried it because everybody, of course, is going to use the criterion in their development that matches with what they're going to get evaluated against. But let's try this. Just make some simple changes so that if you're going to align a person template, you can't do it just on the basis of matching Mr. Similarly, a organization type company isn't enough to organize align organization templates and so forth. And I think we got it to a point where, at least based on informally, going over a bunch of output from the scoring algorithm, we have it right. We're getting the right alignments and not getting garbage, bad alignments. But we're also haven't gone so far that we're unfairly not getting credit for alignments that we should be getting. Okay. Now it turns out we had gotten funded to do a project, which actually funded the work on merging I talked about. The sole point was to spend essentially a year, or in this case a little more than a year, hammering on the Muck 6 task. Just trying to, if you had a whole year, just, given that the participants of Muck only had a month, how far within the current paradigm can we push this F-score? So we actually have the benchmark output, checkpointed output, for 53 distinct system states during the process of doing this. And actually, if you compare every pairwise combination of those system states, a before and an after state, you have a lot of data to look at, 1,378 pairs of systems, where you can essentially compare what the scoring algorithm that was used in Muck it told you happened between those two system states, and what the new, better scoring criteria tells you what happened. Okay. So I'll call them old and new scores respectively. So the first question is, how often did something happen, resembling what happened in the example? So recall in the example, we made a positive system change. The old scorer told us that our results went down. The new scorer on that example would have assigned us a 0 to begin with out of, a number of slot fills, and would have indicated an improvement after we made the change. So how many times did this actually happen? Well, out of the 100 training texts, 47 of them were actually irrelevant. We're not supposed to generate any output. So S-score is always undefined there because your recall has a 0 in the denominator. So there's only 53 texts that matter. And it turned out that 45 of them, or 85% of them, for some set pair of system states, the scores essentially indicated opposite directions. Either the old scorer said you improved, and the new scorer said you went down, or vice versa. So this situation actually happened with a lot of the text. Admittedly, the magnitude of the change was sometimes small. Nobody made any design decisions based on a change of 0.13 of S-score. Other cases, the magnitude was quite large, though. Now, of course, when you're in a process of development mode, you're not really paying attention to changes over one document. you're paying attention to changes as they apply over the whole 100 document set. So first, as an aside, I should note that the natural question that people ask is, what happened to the scores with the more restrictive criteria? And typically the scores just went down, or actually always the scores went down somewhere between, say, 2.25 points and 4 2/3, with an average of about 3.25 points. So that's not an insubstantial movement, although it's not like everybody's score went down by a half or something like that. How this actually would have affected the ordering of the results between sites and muck, is anybody's guess, and you can't recreate it because you can't recreate the process of where people would have done their development, being guided by this new scoring criteria. Between the system states, though, over the whole 100 texts, we did get this behavior where one scorer would tell you that your score went up and the other would tell you went down, or vice versa. It happened in 84 of the cases, or about 6% of these 1,378 cases. Some cases were very small, but others were quite significant. Now, I should tell you that when you're in the 55, 56% range of F-score, you've picked all the low-hanging fruit, right? You don't make changes anymore that make your S-score rise by 2 or 3 points. You hope to get 5 points of S-score out of making 10 changes that all give you a half a point each. You're getting on the tail end of the zip curve at this point. So this is a big number. So between this, in this case, the old scorer would have told us that the changes we made were very negative, right? If the scorer told us that we went down by 2.3 points of S-score, we would reverse the changes that we made. Meanwhile, the new scorer told us that did the proper alignment, said we went up by almost a point. And of course, we would keep changes on the basis of that kind of feedback. Now, even more realistically, what really mattered is the 52 system states, pairs of system states that were consecutive. We generally didn't decide whether to keep changes we made or not based on comparing system 20 to system 2 or something like that. We would look at the last system checkpoint, make changes, and see whether whether our changes improved or decreased performance. So this actually behavior happened in 7 of the 52 cases. And again, we have an example where that's a pretty large magnitude. In this case, the old scorer told us we went down by more than 2 points. We undoubtedly would have reversed whatever changes we made. Where in fact the new scorer told us that we made an improvement, right? So we were probably making changes along these lines where we were getting rid of garbage and the old scorer was telling us that our score went down as a result. So we put back the rules that generate garbage, not knowing that of course, that's what we were doing because all you get out of the scoring algorithm is the number. In those cases, the difference between it was always the old scorer telling us we went down in performance and the new scorer saying we went up. But the reverse happened also. So here was a pair of system states that were a day apart. We ran a system test, we made changes, somebody made a change that day and reran the system. The old scorer said that was a great change. You went up 1 2/3 points, where in fact the true answer was that we actually went down a little bit as a result of the change. So this might have been a garbage generating rule, essentially. So the point of all this is, in fact, these differences really would affect, realistically, how our development went in muck. And certainly would also steer a learning algorithm in the wrong direction. So you get this feeling from all of this that in the 50% range, you're kind of on this plateau. If you have a 20% accurate system, then generating garbage usually helps because it's going to get aligned against something that you didn't generate anything for in a key. If you have an 80% system, it's almost always going to hurt because you're generating the correct output that aligns against things in the key. So your garbage is going to get scored as garbage. In the 50% range, you generate a garbage on some documents where you're generating the right events already, it's going to hurt you. On other documents where you're not generating the right event, you're not generating any events, it's going to help you. What you end up with is, the score telling you, oh, you went up a little bit, you know, a quarter of a point or down a quarter of a point, or, you know, essentially within tolerance, that you got the same result. So actually, it looks like you didn't, you know, nothing much happened, but in fact, a lot of things happened. But because the alignment screwed up, you don't get a clear indication of what direction you're working in. And do you have a question?
Yeah, I was wondering, because I mean, it seems like a lot of this might just be having such a small training set. If you divided your training set in half, for example, and ran it with the same F score on each half, how much you found variation?
I'm sorry, say that. If you split it in half with the same F score.
With the same F score, how much just random variation do you get as your system, as you make changes to your system? I mean, do you find that it all depends on the training data? I mean, is it that specific to that?
It's a fine question. Well, undoubtedly, the larger answer to your question is yes. These are small. I mean, there's a whole question of like how realistic this is to have us all like hacking on 100 training texts, half of which are irrelevant. Yeah, that would be an interesting experiment to try. This whole area is of trying to like figure out what all this stuff means. Different what's the effect of different template structures, different scoring algorithms, different alignment procedures, weighting slots differently. It's way understudied yet, which is okay, except then the numbers are taken real seriously. Like I said earlier, you know, the top 6 systems weren't statistically significant. Now we were actually number 6, right? Now so when we write a proposal, we say, oh, the top 6 systems weren't statistically significant. When the person who scored number 1 writes a proposal, they say, we won Mach 6, right? I mean, so you know, the numbers are taken seriously, even though they really shouldn't be. But that's all you have. But your question is a good one. I don't think anybody's really looked at that. Probably out of fear that it would show that this is all kind of a waste of time. You know, that there's so much variation that, you know, why are we struggling to get another point of F score when we already know 6 points of difference isn't statistically significant? Okay, so I can't resist giving, I'll be closing up soon here, but one more slide, adding to the confusion. So normally, as we said, with the more restrictive alignment criteria, your score goes down, if anything, or it stays the same. If you were getting the benefit of bad alignments, then your score is going to go down. But when I was looking at the data, I was finding cases where the score for the exact same output was going up with the new criteria. Now, how can that possibly happen? At first I'm thinking maybe I have some kind of bug, although I can't measure what that would be. But then I looked at what was going on, it became clear. So remember that this alignment procedure is not guaranteed to find the right solution. It's just searching for the best one. What was happening was that when I make a more restrictive alignment criterion, the algorithm was narrowing the search space in a way that allowed the aligner to find the optimal solution. The solution was there with the old scorer, but because the alignment criteria was so weak, there were more combinations than it could actually try. So the scoring during Mach was actually penalizing us. There were cases, where as much as a 6-point difference. Like we would get a score of 84 on a text when in fact we deserved a score of 90. And this tended to happen on documents that we did pretty well at. So again, you kind of feel this tug towards the 50-60% range. Like if you do better, something like this is happening to kind of pull you down a little bit. And you think, well, how frequent is that? Is that just like a special kind of text that might happen to? But it turned out that at least there was, for 18 of the documents, a full 1/3 of the relevant documents, this happened at least once during the 53 system runs. Okay. So this, you can imagine this, these results have been getting a lot of attention within the information extraction community because I think people realize, as with all metrics, there are problems, but nobody appreciated the extent, to which this was going on. So let me just summarize kind of where to go from here with this, having learned this painful lesson. First, as I just wanted to repeat that we might have to push our learning techniques a little bit. The supervised approaches have not gotten to the point, as I said before, where they're the dominant paradigm. And it's again, as in emerging experiments, you might actually code up a bunch of data for some module in your system and then be surprised at what the real relationship is between what that module produces and say the F-score in this case. And again, no sooner did I generate training data for my merging module than did it become obsolete. A couple weeks later when a couple design decisions were made to change the system. So again, the keys that you do might not be representative and become obsolete. So this that would kind of beg for an approach to what we call indirectly supervised learning, where if it's F-score that we're interested in, well, that's what we use to drive the tuning of the parameters of some embedded module. The positive note to make here is that, well, of course, the keys are representative of what you're interested in because it is the output of the end-to-end task, and they only need to be encoded once. If people change other modules of the system, you may have to retrain your model, but you don't have to recode the end-to-end keys again. And what we should do if we're going to pursue this kind of paradigm is to think hard about how we can design our extraction systems and tasks to do something essentially a little more clever than I was able to do as far as my modeling, right? And Fastest is not such a system, I must say. I'd also like to just push for more attention to kind of these higher level processing tasks in natural language understanding. So, you know, a lot of work still seems to stick to the part-of-speech level, you know, as far as part-of-speech tagging, kind of word level endeavors. And you know, the progress that's been made is certainly been exciting. But as we move away from that to parsing, to semantics, to discourse, we find that the features that we have direct access to in a text aren't so informative anymore. And we have to look to see how we might be able to augment these learning procedures with some kind of knowledge, perhaps acquired itself through some kind of co-training of some sort. Although admittedly, that's pretty pie in the sky right now. I don't have a lot of good suggestions along those lines. But in any case, the role of evaluation, well, point one would be that the properties of the evaluation should not subvert the stated goals of the metric. That should hopefully be obvious. And again, the role of IE evaluation, you know, unlike kind of speech recognition, say, it's only kind of a pseudo-real task. It was really a task that was designed more as much to drive research in a certain direction and to ground people in real data and to cause people to prioritize their efforts than to actually model some real world need. Although there are potential applications for a suitably designed task of this sort, I guess. But in any case, at the current state of technology where we're not producing systems that are accurate enough for people to use, we have some flexibility in how do we set up the tasks so that we can make some progress. And the tasks that have been designed, you know, are questionable in that regard. I don't think they really have a firm idea of what types of research they're promoting when they develop these tasks. Certainly, everybody in the community, I think, agrees, though, that automatically trained systems are a good idea. I don't think anybody that hand codes systems really believes that that's the answer to like the broad deployment of IE technology. So the tasks and metrics, in the spirit of this bullet up here, should really be thought out extensively in order to have more well-defined properties in terms of setting out, you know, search space and so forth than the current metrics have. That's all I have. I'll be happy to field any questions that you have. Finish on time? Almost. Yes?
I was wondering if you could expand on your last comment. and clarify whether you're advocating a return to the knowledge-based kind of systems of the 80s that you mentioned at the beginning, or whether you're expressing, support for this more empiricist, learning-driven. Because you use both techniques in making this point. And you made the comment also that the muck has really shown how far you can get just by using these word level things. Do you think that the technology has now reached a point where we're going to have to return to more grammatically inspired approaches, or that there's still some progress to be made at that lower hanging fruit type level?
Yeah, certainly. I'm certainly not advocating a return to the 80s. Right. That's a lesson learned that should stay learned. There are people in the field who kind of think that, but that's only because that's really what they're interested in doing, and not because I think they really feel that that's where the future is. And so it's kind of like a decade at a time. 80s, we did the knowledge-based approaches, the toy problems. The 90s, we kind of went to the other end, code up data, throw learning algorithm at it. So I guess what I'm advocating now is having spent a good deal of time hand-coding systems and thinking this isn't the answer, and spending a fair amount of time hand-coding data and thinking this isn't the answer, something that's goes beyond both of those, which essentially leads to these, this kind of indirectly supervised learning, unsupervised learning, weakly supervised learning, where essentially you code a little data and bootstrap from that. That's the type of thing. Now, as far as what I was talking about, mining data for knowledge and stuff, I'm not advocating like let's buy psych or something like that and plug it in, right? I don't think there's much hope of that. You could try that, parameterize it and see if you get any information out of it. I kind of doubt it. But maybe some way of kind of doing data mining in a way that you can essentially learn to extract the information that would help. That's admittedly hand wavy. It's more that I'm kind of driven to that view from the history of NLP than to actually having well-formed ideas about how that might go.
So you think there is still more to be learned at this word-to-word level?
Not for this task. Not for this task. The mucks are over, and it was probably, their demise was somewhat overdue, I think, would be a consensus opinion in the community. Maybe not held by the people who were running them, but certainly with the people that were participating in them. It served, as I was telling some of you earlier, it served a great role in the beginning, rubbed people's noses in real data, caused them to prioritize, as I was saying this before. Then the interesting research issues started to come into focus, and instead of like stepping back and now cycling, iterating and shooting for the longer term research at that point, we just had more and more mucks, and people started to play follow the leader. Whoever had the paradigm that worked best in the last muck, like fastest in one muck, next time more sites showed up that had fastest lookalikes. And that's just been happening where people haven't been showing up with anything new or are willing to take risky approaches that might cause them to kind of fall flat on their face. So it's prime time for a paradigm shift. And I think people are this has gone on long enough that people are so restricted in their thinking that they're not thinking out of the box, if we can suffer that metaphor. People are kind of at a loss as to how to go about this next. Precisely because even though we've hit our limit, people's memories aren't so bad that they don't remember that the knowledge-based approaches didn't work at all, really.
About what you were saying about how to get out of that 50% range and the problems you might have in the 80% range. Now, if you were to try a supervised approach or a weekly supervised approach, basically, I think what you should be trying is sort of sort of rules that you know, look at the garbage, as you said, because anything else would sort of like any normal supervised rule that you might come up with. I guess my impression is that by its very structure, it's sort of only going to look at positive test cases and not look at the negatives, right? I don't know if you can comment on that.
I'm not sure if I understood.
In other words,
So certainly the supervised, you know, the corpus of merges, for instance, that I encoded had positive and negative cases in them. And any rule, you know, the rule learning paradigm, the example I had shown. So I'm sorry, why don't you rephrase your question before I...
you want to rephrase it?
Yeah, so why wouldn't...
Well, my basic question is basically having to do with how you would approach the problems that would occur at the 80% level. And
Okay.
because I think that these are, you know, maybe you said this already, but that they're very different from the ones at the 20% level.
Yeah, it's essentially, with this metric, I mean, if they got the metric right and the alignment right, then the problems should be the same. It should be get more good stuff and weed out more bad stuff. And what's happening is that at the lower levels of system accuracy, it's scoring bad stuff as if it's good stuff. So actually, you can imagine having like this component of your system that does nothing but purposefully generates a garbage template. Say, you know, Mr. Fubar at ABC company type company, you know, some garbage event that would actually, and then you could actually have a learning system that determined what the optimal amount of garbage generation is. Now, if the alignment was done right, garbage would always be bad. Would always lower your precision. So that's the main problem.
But I guess what I'm saying is that at the 80% level, the way I would design a rule is, you know, would make that rule be anything you like, but never generate bad stuff, never generate garbage, okay? And aside from that, almost unconstrained or whatever. Whereas at the 20% level, my design criteria would be just the opposite.
I see. Yeah, I guess your rule development never actually kind of works that way, because so at 80% level, again, you're at the tail end of the zip curve, right? The next example, if you were going to take that high precision strategy and write patterns that always worked, they would never match on anything in the test data because they'd be so specific to what you saw on the training data. So what you end up having to do if you want to get any of that tail is to write a looser pattern that's going to get some segment of the tail, but also probably generate output for other stuff that you don't want. I'm not sure if that's answering your question, but it's what you're saying is true, that you might take a different view of how you write your patterns based on what what the level of accuracy is of your system. And in fact, my claim is that people were actually doing that, but unknowingly. They didn't know what was happening when they make these changes to their system, but they were being coaxed in a certain behavior by the feedback that they were getting from the metric. You know, low accuracy, they would write these general loose patterns, and the scorer would say, hey, these are great patterns. And then, you know, later on, those patterns would be hurting them when they got into higher levels of system accuracy, because now they're being counted against them. And that just, you know, that doesn't have to happen. If you get the alignment right, you just don't have to have that confusion inserted into the process. I don't know, maybe I still don't understand. It's relevant to your question, but sure.
What was the ratio between relevant and irrelevant documents in the mock test, actually? Or
In the test,
the
almost the
ratio,
same.
I mean, the number of events that had to be extracted. Because if it was the same, I can easily imagine a system that just a named entity recognizer and fills the template with the names and then put the most probable tag for whatever, and you get like 50% maybe.
Yeah.
Because
Imagine
if
that.
you know how many events you have to generate.
Well, okay, so that's the key. If I did do an experiment a cheating experiment, just for kicks, where I took the mock test, the keys actually for the training data. I still have never looked at the test data, but for the training data, took the keys, took out all the content, put type company, title Mr., and then every company name was Fubar Inc., every person name was Joe Fubar. And that actually, with certain default values put in, actually got a score of 50. I think it was almost like exactly 50. Now the cheating part of that is that, of course, by starting with the keys, I always got the right number of events right, which you weren't going to do. And the whole reason, in fact, the mock evaluation designers knew about problems with potential, people generating garbage as a strategy, and that's exactly why approximately half the documents in both the training and test data are completely irrelevant to guard against that. So they've been doing this for years, but they're still not getting it right.
But still, I would say half of the documents in the training and like 3/4 of the documents in the test should be irrelevant, because if you balance that, you just know, okay,
Right.
for each two texts, I just put one event there, I just generate something,
Yeah.
and it's gonna align somehow.
You could certainly
with
imagine
everything.
so I talked to one person in the field who said, when she heard about these results, she said that she'd always said that DARPA should hire somebody for each mock to essentially do the experiment I think you want to do, which is do as best as you can, except with one constraint. You can't look at the text, or you can look at it in a totally like what you said, maybe you do name recognition and that's it. And then you use that and just see how far you can do, which would then cast. Of course, people don't want to do it because what if you win? And then it just shows that like all of us researchers kind of wasted our time for a month or more. No, it's a good point. And I'd be curious to see how well that does. Or even if you could predict, even if you're not really looking at the text, just that maybe its length, and see how well you could predict how many events to generate from its length. Or some superficial characteristics. Being a cheap thing to try.
I had a non-technical question. You said there were about 10 odd people in the mock evaluation,
Yeah.
and the last one was 97. And what are these guys doing these days?
Oh, good question. Yeah, there were 16 participants in 1995, but nine did the scenario template. Some people just did like co-reference or name identity. There were quite a bit fewer than that for Mach 7 in 1997, and not even we did Mach 7, which is, you have to be pretty confident when you're a government contractor not to do Mach. But I think people have really realized that this has kind of gone on long enough, and people found reasons to drop out of it. Depending on what site you are, you're doing anything from finding a new area to work in to sitting around waiting for DARPA and other places to make up their minds about what's next.
Well, I guess my question was, is there another task that people agree upon which would drive research in?
No. No, in fact, the things that we're starting to hear about is Mach warmed over. Not called Mach, but small twiddles, template filling. Now instead of named entity, they're talking about nominalized entities, like extracting templates from arbitrary noun phrases. Or just intra-sentential relationships, like relationships between entities, but not ones that go between sentences. So just different things. Nobody's found like a new paradigm that was going to drive research. Yeah, people are pretty. There's an extreme lack of ideas along this.
So like, there is the IR end of the problem, and then there is this complete understanding end of the problem.
Right.
Is there any trust from the IR side saying we do more detailed IR? In other words, is that another way to take Mach?
Yeah, I mean, yeah, that's, I think they may have, I think one of the treks may, not 100% sure of this, may have had something that's at least a small step closer to IE, which is essentially sub-document retrieval. So instead of having a huge collection of documents and pulling out the relevant ones, what you have is like the tax manual, and somebody asks a question and you're supposed to pull out the right paragraph that answers the question. Not putting it in a formatted representation, but just something for them to read to try to get the answer from. That wasn't what they actually did in Trek, but I think there was something like that, a kind of a sub-document thing. And that's arguably as useful or more useful of a technology than IE.
Do you have a favorite direction that you think it should go in?
Well, I'm leaving SRI, changing careers, so that's the direction I'm going in. I mean, I'm just being funny. I mean, it's not like, this isn't the only thing that's causing that decision. But no, it really isn't clear, because I think a lot of the people in this community have been so used to having their main goal be F-score that they're almost at a loss for what to do next. I mean, there are other natural language programs at DARPA. There's something called Communicator, which is more of a dialogue management system type of thing. Make travel reservations and stuff like that. There have been tasks, information extraction from speech types of things, pursued and or talked about. But no new interesting paradigm with a new interesting way of evaluating that I've heard about. So really, it's kind of stuck, trying to figure out what to do.
Any other questions? Thank you.
Thank you. Thanks for inviting me.